Ready to begin the semester in 2007. Excellent. Somewhat ready. Okay, my name is Professor Winter, and I'm one of the co-lead instructors for this course. And so we're going to start today by giving a bit of a rundown of the course and the design process. But first, we need to introduce the theme. What is it? Well, watch this. May the torque be with you. Okay, so here is your game board for this year, the X-Wing, and you'll be down in Pappalardo this week for your first lab, and you'll start playing with the board. But to point out some of the key features, well, first, the name of the competition this year is May the Torque Be With You. And do you have a sense of why we named it that? Anybody guess? So all of your actuators in the competition are rotational, right? So if you think of a motor, right, with a shaft coming out of it, and it's outputting a torque, right? How do you convert torque to force? Put a lever arm on here, right, and have a force counteracting it. So if the force is going to be with you, the torque's got to be with you. So, some key features here. You'll start at the lower level of the playing field, here and here, with your robots. And you can see one of the little stormtroopers right here. But you can score points by depositing them at different points around the game board. Each of the 4 shop staff are going to be encased in carbonite in one of these little things that you can pull up out of the game board, and you get points for how high you can pull it. And then as you drive back here, you can't see it in this picture, but there's going to be ramps that go up to an elevator, and you'll have to make the little R2-D2 arm that, you know, that spins things to like decode things. Well, when you spin the elevator lat or switch, you can rise up on the elevator to the second level, and up here you'll have 2 buttons with stormtroopers on them. If you hit one of those, the cantina band is going to pop up behind the Death Star and play the you know, that one. And then at the front here is going to be Darth Vader, and you have to battle Darth Vader, and the way to do it to get the most points is you'll have a lightsaber on each side of this platform that's the same color as your starting box, and if you tip that lightsaber over, that's also a multiplier on your score, and if you tip it far enough and knock down Darth Vader, that's like mega points. Or you can just push Darth Vader off and get some smaller points. So, yeah, and I hope you can see that's the Death Star behind. But yeah. Awesome game board. The shop staff has outdone themselves with this thing. This thing's nuts. I also forgot to mention, I am from New England. I grew up in New Hampshire, and yeah, I'm sorry for all of you that are from outside of New England. Well, not really sorry, but yeah, whatever. So I can't be in the parade today, because the parade's going on right now, so I have to kind of do the parade while we're here. Are you from New England too? Yeah. Nice. All right. So next, I want to give you a bit of a rundown about the course with a documentary that was made 2 years ago telling the history of the class. So here we go.
So from the beginning, 2007, 270 was about building a device to accomplish a task. Originally, it was kind of rubber bands and tongue depressors and paper clips.
You had springs, you had wood, you had metal, and you build a mousetrap.
This is a mechanical engineering design class at MIT.
We give each one of them a kit of materials. The students call it a bag of joke. But we spent quite a bit of time thinking about what's in the kit. The task is really to grab this peg and try to put it into that square hole.
The competition is very tough, and the ideas over here were really incredible.
The real innovation was to make sure that you not only designed it, but you built it.
It's the class I've been waiting for. I think it's the class that every mechanical engineering major wants to do, like, as soon as they declare mechanical engineering.
The reason why I chose mechanical engineering is because I like making things. This is the class where you make things.
This is what I went to MIT for.
It's the first time many students at MIT are coming in contact with the big machines and the workshop. And this is really the class where you take everything that you learned in those lecture halls and you put it to use.
Okay, it is time to design.
They won 2 years ago, too.
And I think it embodies the spirit of MIT. It's the first experience students have designing something on their own.
I'm starting to see how what I'm learning applies to the real world.
This class represents the MIT's model of mind and exactly.
So the theme this year is Hack to the Future, which features a giant DeLorean on the game board.
We build the competition around good mechanical engineering principles like climbing hills, optimizing power, managing friction, but all the time mix in cutting-edge new engineering innovations.
Now it's chips and electronics as well as things like 3D printing.
They actually have to program the robot using microprocessors.
It's what the world is doing right now.
This is such a real-life experience for the students. They're making something that works perfectly on paper and then performs terribly in real life. And that's what happens to all of us as engineers. This class is as techie as you get, creating physical objects that can operate in the physical world. And I think that is the core definition of what mechanical engineering is.
Some of the stuff that stayed the same is the wonderful way you compete like crazy, but help each other in the process.
You'll take out time from working on your own robot and help someone else with theirs.
Good job.
At the end, you celebrate for students, you like celebrate what you did and you showed it off.
I definitely feel more like a mechanical engineer.
The enthusiasm and the passion that students have to build these robots, to get down in that machine shop, get their hands dirty, and build real things. This is the true spirit of 2007.
All right, are you guys ready for all that? Yeah. We're going to have a hell of a semester. Okay, so let's go over what this course is all about. What we're trying to do here is build up your competence as design engineers and your self-confidence to be able to use that engineering theory in practice. So we're going to stress the creative process and the design process. We will guide you through that process as you make your robot. And we're really going to stress combining analysis, which you learn in many of your classes, with the synthesis of that analysis to be able to employ it into new designs and new creations. Right? So you're going to do things like creating, you're going to do lots of creating, evaluating your designs, doing analysis mathematically to analyze your designs, applying a lot of knowledge from a lot of backgrounds to this, understanding what you're doing, and hopefully remembering this and bringing it forward into your careers. Now, as far as the course staff, we've got a ton of people that help out here. Here are all the lab instructors that you'll be working with. Danny Bronstein runs the Pappalardo Lab, and he has a whole career in product design, so he's a major design guru. Shreya Dave graduated from our department with a PhD a few years ago and is starting a company that's designing products. Matt Duplessis runs 5Wits, and if you guys ever visited Tomb or near Gillette Stadium, there's also like this interactive, like kind of funhouse type thing. I don't know how you describe it, but go to it. It's awesome. So he designed all that. Ben Gallup works for Atlas Devices, which makes like Batman-esque rope ascenders to climb up buildings super fast. Sangbei Kim is my brother from another mother, the other co-instructor of this course, and he makes all kinds of crazy, awesome biomimetic robots. Dan Kleck, I actually don't know, is Dan here?
Hi.
Dan, what is your background?
I graduated in 09 from MECI, got a master's in 12, and now I'm trying to start a robotics company.
Awesome. Also designer. And potter, apparently. Captain Chip McCord, our captain of moral values in this course, is a master of naval architecture. And Alex Taché designs all sorts of cool things with fluid systems, like propellers and fish fins and stuff. And then I like big trucks. And also like designing crazy things. Our other course staff is the Pappalardo staff, which will help you build your robots. Now, on the scale of value and priority you put people in your life, put your mom, number 1, and put these guys as number 2, right? These guys are the glue that keep this course together. They make the playing boards. They're down in the trenches with you, teaching you how to design and make things. They are awesome. Best resource to this class. Our course admin is not actually a robot. She's a real person, Maral. And then our 3 TAs this year are PK, Larissa, and Vrushank, who you'll be interacting with a bunch. Now, as far as grading, you have 3 primary assignments, types of assignments that constitute most of your grade. The first is milestones. So every week you'll be assigned a new milestone assignment, and these are meant to guide you through the design process. You'll document them in your design notebook, and they'll be graded by your lab instructor. Through the first 5 weeks, you will also have, in the 9th week, you will also do an oral design review for milestone 9. Then you'll also have physical homeworks through the first 5 weeks, and I'll talk about those more in a second, as well as written homeworks through the first 5 weeks. We will do 10 pop quizzes throughout the semester. So attendance in lecture is required if you want to get this 10% of your grade. And then finally, your participation is 10% of your grade, and your lab instructors will talk about this, and we'll talk about it all together, how you participated in lecture. And if you don't finish a fully functional, competition-ready robot and impound it at the end of the semester, so you're ready to go in the competition, you get 0% participation grade. And this is to teach accountability. Right? We want you guys to finish your designs and have them work. You don't have to take pictures of this, by the way. I'm going to post this right after lecture, so you can download these slides. So let's talk about the major grade components of this. The first is the milestones. That's the biggest part of your grade. And the objective here is that this is giving you practice and guidance through a design process where you go from ideation all the way to creation of a new machine, and to make you practice this analysis plus synthesis in order to create your robot. There'll be 11 assignments, 11 total milestones, and you're going to progress from a conceptual, like high-level strategy to the actual physical conceptualization of your robot, to developing the most critical part of your robot, to integrating all the modules together into a full machine, and then iterating that process and ending up with a final competition-ready robot. The second is these physical homeworks that we do. And the objective here is that we want you to physically implement the lecture content you're hearing here in 10250 down in the lab. So you're going to build this little mini-me robot, and I'll show you that right now. Next week in lab, you're actually going to design it this week. Let's pull this little guy out of here. So here's the mini-me. Super duper simple little robot, and I can throw it on the overhead so you can see it. So it's a platform made of ABS that's bent to hold 2 motors, and there's a caster wheel here, and you can slap a battery on this guy and drive it around. Let's put this on. So right in the second week of the competition, you're going to have a robot that is actually ready to drive on the playing field. And then in the third week of the course, you're actually going to be scoring points with this little guy. So in the first 3 weeks, at the end of that, you're going to have a robot that you could put right into the competition and score more points than 0. And actually do pretty well, because a lot of people end up scoring 0 points. So, you know, this is just a little robot guy. And, you know, driving this around the game board teaches you so many principles that would be hard to capture mathematically or in CAD. You know, like say there's a little, like, thing in the game board, like a crack between 2 pieces of wood. It might be hard to drive over that. And you might not have realized that at first looking at the game board. You'll also find out that these things may move kind of slow, and you might want to speed up your robot, and they can be pretty finicky to drive. So you can learn all of that with this little device. And this exercise of the Mini-Me will help build that competence and confidence to be down in the lab, use the machine tools, make your own stuff, drive on the game board, all this great stuff. So you're going to have 5 problems that go through CAD design, bench level prototyping. You're going to do hill climbing to see how you can prevent your machine from tipping over backwards. You're going to do some motor power testing to really characterize the motors that you can put in this guy or your real big robots. And then also you're going to make it autonomously drive and score points. So at the end of all of these, you're going to have multiple ways to score points in the competition and already have a little robot that's ready to do it. And then the final big part of the class is the written homeworks. And this is a critical part of the class because this is where we get to present to you real life design challenges. Like, you know, when all of us who teach this class go into the real world and look at a design problem, it's not like somebody writes out a homework assignment and says, calculate the center of gravity here and blah, blah, blah. No, it's an unbounded problem. You have to think about, okay, what is going on in the problem? What are the forces, power, momentum, blah, blah, blah? And what theory could I apply to that problem to figure out what's going on? Right? So this is going to give you a taste of actual real-life design problems. And we make a great effort to give you like real-life machine problems. So this was about an airport tug to pull a plane and how it gets traction by the plane putting a big load on the tug. This was about tipping over a forklift and like using real dimensions of a real forklift. So you're going to do these through the first 5 weeks of the semester, and they'll be graded by graders in the class. The next thing is, after class today, if you haven't already done this, go out and get yourself a design notebook. So, hand to heart, right before I came down here, I dragged this thing out of my backpack. I carry this thing everywhere I go, anywhere in the world. And, you know, when I'm working on stuff, you got calculations of things, you've got schematics of things. This is for a well project that I was working on for a company. You know, I'm signing and dating everything. We're going to teach you good notebook practice because it's really, really important that you document your work as an engineer. So please, please, please go out and get that after class today. Other course info, when in doubt, check out Stellar. We post all our info up there. We don't have a textbook in this class, but we do have a lab fee to cover all the kit materials, because your kit materials are, you know, multiple hundreds of dollars. Your milestones and physical homeworks will be assigned in your lab and then due the next week in your lab. So each lab section will have a different due date depending on when their lab meets. But your written homeworks are all going to be assigned on Sunday and due the following Sunday. And they will be graded by course graders that we hire for the course. We're going to have homework reviews that will be conducted by the TAs, so they will review some of the class content we go over and help you out with approach to the homework problems. Those are going to be held Thursday afternoons, and the TAs will announce the time. Actually, Thursday evenings, right, TAs? Yeah, it'll be after 7, so athletes can attend. And then labs start today. If you are in a Tuesday lab, I will see you down there at 2 p.m. to start our labs. If you're in a Monday section, you have to come to one of the other lab sections this week so you can get your lab up and running and get your locker and start your first assignment. So on Stellar, you're going to find 2 documents that I want you to read. The first is our subject information and policies. This tells all about the course, tells all the people in the course, our contact information, the grading, all the assignments, and how they're graded, blah, 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 blah. So please go check that out. And then the second is our course calendar, which is a much more concise document. I'll put that up here. So if you look through here, it tells you when all the milestones and physical homeworks are due, when your written homework is due, and it tells you what content we're going to go through in each lecture and cover, and that is then the content that we're going to put into the written homeworks. Now I want to point out a few things. That first, the class is very paperwork heavy in the first half of the semester before spring break. Because at that point, you guys are just kind of getting rolling in the lab. You're mostly just making simple, quick bench level prototypes or little mini-me's. So we're using the time allotment for the class to be written work heavy in the first part of the semester. But then by the time spring break comes, your last written homework is due, actually the week before spring break. Or not the week before spring break, but the week before that. So the actual week before spring break, you can finish up your most critical modules. And then after spring break, we are just full throttle building your robots to the competition. So we have no more written assignments other than the milestones, which you'll do in your homework. And then we have a bunch of lectures to teach you about real-world design and applying all the content you've learned in this class to real-world design problems. So this is a lot of fun. And I think with this structure, we balance the workload, because as you all know, if you've ever built something or been in a project class, the big rush is at the end of the semester. So we do a gentle big rush in the beginning of the semester with the written homework, then dial that back so you can really go hard on the robot building in the end. Okay. So all that again is on Stellar. All right, so now it's time to learn. Let's talk about design process. So why might we go about a process of design? You know, why not just conjure something out of thin air and then make it, right? Well, the reason is design doesn't work like you have a great idea, you make a Saturn V rocket, and you go to the moon, right? Try to picture a Saturn V rocket in your head. Not just this shape, but like the O-ring in one of the thrusters at the bottom, right? This thing is like taller than a football field is long. It's massive, massive, massively complicated. And so people just don't have the cognitive ability to carry all of these details in their head. They have to break it down to smaller, more tractable parts. So design does not work this way. And we're going to teach you a process. So I want to use kind of a case study to show the design process. And this is a little series I want to do in a bunch of my lectures this year of profiles in design and innovation. So what's this picture of? Wright Brothers, yeah. Unless you grew up under a rock, you've seen this picture, right? It's one of the most famous photographs ever taken. And these guys were successful making the first powered aircraft because they were brilliant designers, brilliant in their design execution, and I would argue like the best experimental scientists ever. So let's talk about what they did and what they did in their design process. So the first point that I want you to remember is a design process enables you to break up a big problem, big Saturn V type problem, into smaller, more tractable chunks. So when the Wright brothers, Wilbur Orville, started thinking about flight, it was 1899. And Wilbur started reading about people who were playing around with aircraft, gliders and aircraft. And their benchmark was this dude in Germany named Otto Lilienthal. And he made these bat-wing type gliders, right? And he'd make the things, he'd jump off a cliff, he'd glide around, and eventually he died because he crashed into the ground. And the Wrights were like, that's nuts. We don't want to die making these things. And then the other thing they realized is, well, actually, I'll tell you that in a second about Otto Lilienthal. So instead of just making a whole airplane or a whole glider, they broke it up into chunks. And the first chunk they worked on was lift. So going back to Otto Lilienthal, he published some tables of different wing geometries and how much lift they should give depending on how much drag they were experiencing. So given a velocity going through the air, they could calculate how much lift to how much drag they would have. That's very important in aircraft, lift to drag ratios. So the Wrights started playing around with this. They actually made a glider based off Otto Lilienthal's designs, and they were like, wait a second, this doesn't work. This theory's all wrong. And this is a pivotal point, and I think really shows how brilliant these guys are, because they looked at the leading theory about aircraft design and realized it was wrong. Right? If you went to your backyard and made a space shuttle and went to the moon, I don't think that's as big an accomplishment as what these guys did, because space shuttle theory exists. Right? You can look that up in books and read it. These guys started with nothing, and worse than nothing, wrong theory. So instead of making a bunch more gliders and killing themselves, they were like, no, this is crazy. What we should do is test a bunch of wing shapes and characterize their lift to drag ratio. So they made this little balance and put little wings in here, and they could measure with an airflow how much lift versus how much drag they have. They actually made the second wind tunnel ever in the United States and ran it off an internal combustion engine they made themselves. And this, by the way, is made all out of like bicycle parts and stuff, and it's accurate to within 10% of modern equipment. These guys are badass, right? So they figured out lift, and they started making gliders that flew pretty well, and they were matching that analysis they were doing in theory to the actual performance of the glider. So then they had to figure out control. And because, you know, a plane doesn't just fly in a straight line, it turns. And their contemporaries at the time were thinking that planes would fly through the air like a ship goes through water, right? It'd just stay on a plane and make a turn. But if you make a turn in the air, what happens? What happens to your outside wing versus your inside wing? Yeah, you get more airspeed on the outside, less on the inside, and you go and crash, right? You want to roll over. And so the Wrights were the first ones that realized that if you need to turn, you need to bank as well, right? And do banked turns. And they made the first rudimentary ailerons, and they did it by warping the wings. So, you know, that edge would go down, that edge would go up, and they figured out control. So the theme here is they took this big intractable problem of powered aircraft and broke it up to first lift, control, and then the next part was power. Now, because they characterized their wing shapes, they could calculate how much thrust force their plane would need to get enough lift to get off the ground. So they could figure out how much power they needed to push through the plane through the air. And they calculated they needed 8 thrust horsepower, and they figured they could get about a 66% efficient prop, so they needed 12 mechanical horsepower out of an engine. They searched around, they talked to a bunch of engine manufacturers to make a lightweight engine that they needed. Nobody would do it for them. You know what they did? They made it themselves, because they are that badass, right? They made their own super high power to weight ratio engine, and all the contemporaries at the time, when they talked about propellers and propeller design, they said that airplane propellers would be designed just like ship propellers. So, you know, being good students, they looked in books to try to find how ship propellers were designed. Turned out they were just designed by rule of thumb. There wasn't any theory behind them. So the Wrights figured out that a propeller is just a wing traveling in a helical path, in that your airspeed changes. It goes slow from the root to high out at the tip, so you want to change your angle of attack. And they ended up making the most efficient propeller ever made for the Flyer. They put all of this together, and this sucker worked basically on the first try. Unbelievable. The only issue they had is the propeller shafts were kind of weak and they could break, but they fixed those, and this thing basically worked. And it only worked because they solved this massive, crazy problem one step at a time, did the analysis, did the testing, and then brought all of those modules of the design together to make the working aircraft. Now, in contrast, their big competitor at the time was this dude named Langley. And that name might ring a bell from Langley, Virginia, because it's named after him. This guy was the head of the Smithsonian. He had like infinite resources available to him, and he would make aircraft, these wonky biplanes, that he would launch off a floating platform in the Potomac, and they'd just launch and crash, launch and crash, launch and crash. And so he did not follow a good design process. He built a whole plane, wrecked it, and then started again. Unlike the Wrights, which mitigated their risks by breaking it up into little parts and putting it together. So a fun backstory about this is that a number of years after the Wrights flew, the Smithsonian was kind of ticked that their guy didn't fly first. So they hired the Wrights' competitor, main competitor, Glenn Curtiss, to retrofit this thing and to get it to fly. So he put a bigger engine on it, and he flew it really close to the ground in what's called ground effects, where you can kind of pack air underneath the wings, between the wings and the ground. And he did get it to lift off the ground. And so the Smithsonian jointly credited the Wrights and Langley for co-inventors of the first powered aircraft. And then they asked the Wrights, may we display your Flyer in the Smithsonian? And they said, hell no, until you credit us as the sole inventors of the first powered aircraft. And this feud went on for a while, and it was eventually resolved in like the 1930s, when the Smithsonian finally said, okay, Wilbur was dead by that point, but d'Urville said, okay, we will credit you as the sole inventor, and there's a condition that when this thing's displayed, there's a plaque that says, Wilbur and Orville Wright were the sole inventors of the first powered aircraft. And what's crazy about this too is this thing should have been destroyed in a flood in Dayton, Ohio, and it wasn't. Then it was shipped to the UK to be displayed in their Smithsonian equivalent. They couldn't ship it back to the US until after World War II because of the danger in the shipping lanes, but it did get back to the US, and you can see that exact flyer at the Smithsonian. I go there and just bow down every time I see it. Man, that is like the most holy relic for engineers. Totally go check it out. So another